Hello and welcome to the discussion of parallel circuits. It is week 6. We're doing parallel circuits. You guys need to know this stuff because it's on the exam. It's pretty seriously on the exam. Today what we're going to be discussing is kind of series circuits. We're going to be talking about Kirchhoff's law, but kind of in reverse. It's a little bit different. And I think one of the things I'm going to highlight today is the fact that I need you guys to start using the memory on your calculator, because if you don't, you'll lose marks on the exam. Awesome. All right, good. So here we go. Mr. Kirchhoff, a really cool dude. Okay, so he's way back in 1824 and 1877. He was a German physicist, and he studied light, thermal energy, electric circuits, and current laws and voltage laws. So we're gonna focus on voltage laws and current laws. He studied circuits. He already knew about Ohm's law. He was like, yeah, Ohm's law, that makes sense to me. He took Ohm's law and he studied circuits, and he did some amazing things. He studied series circuits and he studied parallel circuits, and he defined the difference between the two of them. So welcome to parallel circuits, and we'll be taking a look at, we're going to learn how to identify a parallel circuit. We're going to determine the voltage across each parallel branch, something called branches in parallel circuits, and we're going to apply Kirchhoff's current law to parallel circuits, determine a parallel resistance. This, I think, is probably the most fascinating part about this lecture. We're going to apply Ohm's law in parallel, and we will see that Ohm's law applies everywhere. No matter where you look at it, no matter what, even if you had a parallel series circuit, you can apply Ohm's law the same. And we're going to use parallel circuits as current dividers. Last week, we did series circuits as voltage dividers. This week, we're going to do parallel circuits as current dividers. Pretty cool things. And we're going to take a look at power in parallel circuits, which is possibly maybe the coolest thing. This determine the total parallel resistance is fascinating. It's actually really fascinating. But this is kind of cool. This is kind of almost magic. Determine the power in parallel circuits, almost magic. So let's continue on here. I'm going to do this, and yeah, let's jump through here. So what we're going to say here is resistors in parallel, okay? They're these paths, and we call them branches, okay? A parallel circuit is one that has more than one branch. So if we take a look at the current has an option. This is electron theory. This circuit comes from the book, and the book's in electron theory. There's a circuit path that goes from negative. The current goes here, and it can go through here to get back to the battery, or it can go through here to get back to the battery. It has two options. A parallel circuit has more than one option for the path of the electrons. And we can see in this case there are a lot of them. Let's take a look at some of the terminology. Here we've got the total current. The current going through here is IR2. The current going through here is IR3 and IR4. It's different than the total current. Pretty cool. Okay, so dude, these are really cool. These are parallel arrangements. I was trying to think of the most complicated parallel arrangements, and I couldn't think of much more than this. These are all parallel, because if you take a look at it, obviously the current going from here to there, it's got two paths. From here to there, it has two paths. This is a wire. It's just a piece of metal. The electrons go through this. The potential of the electrons go through this instantaneously. And then the current travels this way and this way. So just because this is a long path doesn't mean it's any different than maybe even this picture or that picture, or even this picture, because there's a long path here. These are two series, two parallel, two parallel, two parallel, and here there are three parallel, and here there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 in parallel. Here there are 3. 1, 2, 3 in parallel. Now this one's kind of funky, but it's still all in parallel. Look, if I'm an electron, I have an option to go from here down to here. How many options do I have? Well, one is I can go to here, I can go down to here, and this piece of metal all the way along here and all the way along here is one potential point. It's not like the electrons have to travel very far to go through here, because the resistance of this piece of metal is theoretically zero. So pretty much I just have to go from here to there, or from here to there, or from here to there, or from here to there. This is a parallel circuit. Pretty cool. Okay, good. So the definition of a parallel circuit: if there is more than one circuit path or a branch between two separate points, and the voltage, so this is interesting. So if we're studying a circuit and we see that there is more than one branch, and we also, through study, see that the voltage between those 2 points also appears across all of the branches, then we have a parallel circuit, okay? Then there is a parallel circuit, and essentially that's what's going on, and we will see that the voltage across all of these is the same. Pretty cool. And here we go. I mean, this is just essentially taking a look at the meter itself and saying, let's take a look at it and just read it. So if we do put a meter on here and we have a 12-volt source, then the voltage drop across each one of these is 12 volts because they are in parallel. When we were doing them in circuits, and when we were doing the resistors or the loads in a circuit in series, they shared the voltage. In this case, they all have the same voltage, but you'll love this, they share the current. We'll get into that in a minute. Okay, again, here we go. So what's happening here is that when we take a look at the current going through R1 plus the current going through R2 equals the total current coming out of the source. So the total current coming through here hits this node. I'm going to call this a node. It hits this node, and the current itself splits up. Some of it goes this way and some of it goes this way. As we know, current is just charge per unit time. So I've got a certain amount of charge coming out of my power source. It hits this. Some of the charge goes this way and some of the charge goes this way. Now, how do we know how much goes here and how much goes here? Dude, we use Ohm's law for that. I will show you that in application. So Kirchhoff's current law, when he studied this stuff, he found that the sum of the currents into a node, the total current in, is equal to the sum of the currents leaving the node. So if I had 2 amps coming in here and 1 amp came down here, you can be sure 1 amp is coming down here. There you go. So this is just a basic example, and this is a little bit of math here where we're taking a look at Kirchhoff's current law. Kirchhoff's current law says that the IT equals the IR1 plus the IR2. It's that simple. IT equals IR1 plus IR2. In this case, we know that's 5 and we know that's 12, so the total is 17. It's just that simple. And that's the nodal point A. So this is a nodal point A, and that's a nodal point B. These are things that are important in parallel circuits, and especially when we get into series parallel circuits, where we got to talk about certain points in a circuit, because in this case, we can see that this point is doing something. It's dividing the current. Okay, good. So here we go. Kirchhoff's current law can also be stated like this, where we're going to say the total current minus the current going through one of the branch, minus the current going through the another branch, minus the current going through the last branch is going to be equaling to 0. Another way of looking at it. So now the total parallel resistance. Okay, I'm just gonna stop here for a second, guys, before I move on. So what we just found out was that in a parallel circuit, the current is divided kind of like in a series circuit, how the voltage is divided, but it's backwards. So in a parallel circuit, the voltage is shared. Everybody's got the same voltage, and the current's divided. In a series circuit, everybody had the same current, but the voltage divided. Voltage was divided. So they're kind of inverse, and we'll see that. Like, I mean, you've learned series circuit. That's kind of like your foundation. We jump into parallel circuits. Everything's backwards, and we'll see that the total resistance is also totally backwards, and it's so cool. It's fun to derive the formula for parallel resistors. I don't think I have time for that, but maybe I will figure it out. Maybe I'll do like a quick little video on it because it's fun. Okay, here we go. So what I'm saying here is that if we take a look at the total resistance, now just really stop, because I told you this is the coolest thing about this lecture. Think about this. If I had 10 ohms, 20 ohms, and 30 ohms, what I'm doing is I'm adding more paths for the current to travel. Okay, let's say I had a power source here. Okay, this resistor would be drawing current. Okay, so if I had a power source here, this resistor would be creating current, would be drawing current. If I added a resistor, it would also draw current. If I added another resistor, it would draw current. So therefore, the total current going through my circuit increases the more branches I add. Let me say that again. For every branch that I add, it draws more current. So therefore, the greater the branches, the greater the current. And we know through Ohm's law that current and resistance are inversely proportional. So therefore, if the resistance sorry, I'll just say it with the current. If the current goes up, the resistance must have gone down. When resistors are connected in pair, the total resistance of the circuit decreases because I'm drawing more current. For it to have more current, obviously the resistance decreases, the total resistance decreases. The total resistance of a parallel circuit is always less than the value of the smallest resistor. And what this means is this. I'm not going anywhere. Just bear with me here. Again, let's just say I won't forget about this 20 and that 30. They're not there. This is the only resistor in the circuit, and it's drawing current, okay? If I add a resistor, the total resistance is going to go down. You know what? It doesn't even matter what the value of the resistor is that I add. The reason it goes down is because it's drawing more current. Ohm's law says the current and resistance are inversely proportional. So, and when I show you the formula, this might actually make some sense. Good. So going through this again. If I add a resistor, I'm going to add more current, therefore the total resistance goes down. So if my total resistance was 10 because there was only one resistor that had 10, and I added a resistor of another 10 or even a million, the total resistance would go down because the current went up. That's it. So we can always say, if you were to calculate the total resistance of this circuit and you got a value that was greater than 10, you know you're wrong. If you got a value that's less than 10, you're thinking, yeah, it's probably correct. Okay, moving on, let's take a look at this. Now, this is the concept of adding resistance in parallel, and it starts with conductance. Okay, so conductance is the measure of the ability of a component or a circuit to conduct. Okay, so essentially what's going on is that something is in a circuit, or there's some circuit, and its ability to conduct is inversely proportional to its resistance. Now, we talked about that several lectures ago. So what I'm saying here is that just even, actually that was the lecture, I didn't do that video, which I haven't done yet. But dude, just go over the series video of me doing series circuit and you'll get it. So here we go. So what's going on is that as I'm adding these, as I'm adding more resistors, each one has a certain amount of conductance. Even though it's inversely proportional to resistance, the more I add, the more conductance. So we can see that we can say that the total conductance of a parallel circuit is the total G is equals to the G of 1, G of 2, G of 3, G of 4, and moving forward. So if I take a look at that, and we take a look at this here, if I studied this in conductance as opposed to resistance, I can say that the total conductance is this. Because, dude, if I'm adding more branches, I'm just adding more places for the current to flow. So it's becoming more conductive. Okay, good. So what's going on is that, therefore, the more of these I add, the greater the conductance. The conductance increases because I'm adding all of these components, which are called resistors, but they also have conductance. They're allowing more current to flow. Now, we know that conductance and resistance are inversely proportional. If you don't know that, we'll sit here for a second on this slide. The concept of conductance is just the opposite of the concept of resistance. The actual symbol for conductance is a capital G. The unit for conductance is a Siemens, which is a capital S. As you know, the symbol for resistance is an R. The unit for resistance is an ohm. We know that as conductance goes up, current goes up. Okay, so that makes sense. If conductance goes up, current goes up, because if the property of the material that is the current's going through it, if it conducts more, the current will go through it more. There'll be more electrons flowing through it, more charge. Now, resistance is inversely proportional with conductance. We have that concept here. And conductance is inversely proportional to resistance, either way you want to look at it. Okay, good. So now, let's just actually, that's just fun. I like to do this formula, dude. This is fun. We know this is true, and we know that is true. Okay, so I mean, I hope this makes sense. If this doesn't make sense, rewind the video and just wrap your head around that. But moving forward, if we have this formula and we know this, then we can do some pretty cool things. This is actually exciting. Like, I'm so excited, I want to cry right now. Like, you guys have no idea that, like, the power of what you're going to learn right now. Watch this. Okay, now, if this is true, if this and this is true, I can replace everywhere I see a G, I can put 1 over R. So I'm going to say the total conductance is 1 over R1 plus 1 over R2 plus 1 over, because that is, I'm just substituting the R in here. Now we'll take one more step, and I can say this, because dude, look at, I mean, you know that as opposed to writing 1 over R, I can just write R to the negative 1, R to the negative 1, R to the negative 1. So let's take it one more step, and I can say, hey, if the total conductance is equal to inverse of total resistance, I can now say 1 over RT is equal to all of this. Here's where the beauty comes in. It's so beautiful. There you go. That is the nice, easy, quick formula when you're using your calculator to calculate the total resistance of a circuit based on conductance. If you have ever seen that formula before, or know this formula, or if you've ever seen it like this, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, you know where it comes from. Now, this is a nice, quick, easy way to do it on your calculator. If you do not do it like this on your calculator, then you're not going to get an accurate value, not at all. If you calculate 1 over R and then write it down on some piece of paper somewhere, calculate 1 over R2, write it down, it's going to be 0.00123, whatever, and all of these different values, and then you add them all up, and then you find the inverse of that. Dude, that's crazy. Just do this all in one row. So the worksheet has like so many of these, practice, 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 and I need you to do that. Let's take a look at this. Okay, before I even go there, I'm going to say that in this case, absolutely 100%, the total resistance is less than 300. It has to be, because the lowest resistor here is 300. It's actually all the same. It doesn't matter. It's less than 300. So I'm just going to write it in. I'm going to write down the formula. I'm going to fill in the answers, and I'm going to write down the answer. And the answer is, you're going to use the calculator. Type it in exactly as it's seen in the calculator. Use this inverse button, because that's to the negative 1. So you're going to type in 300, you're going to hit that. Or you're going to hit 300 and hit that. Every single calculator, every single calculator has an inverse button. It'll either look like this or like this. Just type it in and then put a bracket and then hit the inverse button again and press enter, and you're going to get that. Exactly. So if these values are all different, you'll still be able to get an exact value if you do it all in one formulation. Now, let me tell you this. On the exam, I give you one of the questions about calculating the total parallel resistance. You have to give me the answer to 6 decimal places. Yeah, like it's a mark for giving me to 6 decimal places. So what I'm saying right now is, if you do not use your calculator like that, like I just showed you, you're not going to get that answer correct. Learn how to do that. It will save you so much time and energy, because you're going to be doing it a lot. Okay. So yeah, like over and over and over and over again. So just go to the worksheets and just do all of those questions over and over until you get it, until you're like, oh yeah, that's actually pretty simple. No, it'll actually turn that way. Okay, moving forward. Here we go. So we've looked at that and we know how to do that. You guys are experts at that. Let's just move forward. I don't talk about it anymore. And this is just another example. So in this case, I know my total. I'm going to back up. If I know my total resistance that's 46 kiloohms, mega ohms. Absolutely. The total resistance is less than 4.6 kiloohms. I know that, I think my brain said 46 kiloohms. It's less than 4.6 kiloohms. Dude, I'm not kidding. You have to type this into your calculator. You have to learn to do this. Just practice it and practice it until you get it perfect. Because I know that 4.6 kiloohms, you can type in 4600. You can do that if you want. But I need you to practice to do this. Use engineering notation, 4.6, and then EE 10 to the 3 or EE3. Practice that and do this, and then you'll have to do it for this one, unless you want to actually type in that many zeros, which will screw it up. So, and then the answer is this. Great. That's it. So your calculator is going to show you this, okay? If you don't get this exact, try this. I'm not kidding. Try this example. If you don't get this exact value, you're not using your calculator right. I always want 2 decimal places of accuracy in the answers you write on any exams or any tests or any assignments. I want 2 decimal places. And by the way, I guess I have to tell some students this, surprisingly. If this was a 6, you would write down 8-6. Not 8-5. Because this is a 1, you would write down 8-5. I'm sorry, yes. Some of you guys are going like, dude, We know that. Seems some people don't. Okay, moving forward. Now, this is another way, okay? This is called product over sum. If you want to use this, it works well. You can do this with 2 resistors. There's actually a product over sum for 3 resistors. It gets a little bit complicated. I'm just telling you, guys probably know this formula. Some may know it, some may not. I didn't even suggest using it because if you just type in the numbers in your calculator like this, it's a lot quicker. There you go. Product over sum. You can use it if you want. Now, here's an example here. We're calculating the total resistance with product over sum, and there's the answer. Okay, good. So now that was 683.30. So this is just another thing. But right, the total current. Sorry, let's jump into Ohm's law. So there we go. Hold on a second. So what we've just done so far in this is I've talked to you guys about the fact that series and parallel are different. They're kind of inverse to each other. Parallel does everything kind of backwards to series. We know that it shares the voltage. It divides the current. In series, it divides the voltage and shares the current. In parallel, we know that the more resistors we add, the lower the resistance gets, which is weird, but it's true, and the math is there, and the practicality is there. If you need to understand that again, back up with the video and wrap your head around that. I told you at the beginning of this that Ohm's law works always. No matter what you're talking about, Ohm's law works. All we need to do is understand Kirchhoff's laws to help us apply Ohm's law. I want to show you how to apply Ohm's law to a parallel circuit. Let's jump in. Okay, so here we go, and we jump in. We have an example, a real basic, simple example with 2 resistors. And how do we do Ohm's law? Calculate the total current? Well, I would say that I would find out the total resistance first, and then I would just use Ohm's law. So let's take a look at how I solve this particular problem here. So we know that I'm going to write this formula here. The total current with my subscripts is equal to the total voltage, or the voltage source, divided by the total resistance. Okay? Nice and easy. Now, if I want, I can actually, because it's a simple formulation, I can write my total resistance here. So now this is my formula that I'm going to start with. I'm going to fill in the formula. I'm going to fill it in with units, volts, and ohms. And get this. You can write ohms out here. When you're doing your calculations, just like I did up here, don't put ohms in here, because if you're going to, you have to actually put ohms inside the -1. You have to put it inside this bracket here because we have to do the math to the units. So just put ohms on the outside, because again, I'm doing math with the units. So going back down to this example here, this is how you put your units in. You're going to say 10 volts divided by this many ohms, and that's what your calculator is going to say. Now, always write it down in milliamps if you can. Okay, good. So in this case, it's 279 milliamps. If you wanted, you could put 278.75 milliamps. I'm just showing you an example to say that you can do that. Now, I'm going to check, because I'm going to calculate the current through here, and then I'm going to calculate the current through here. I'm going to add those 2 currents up, because I know Kirchhoff's current law says the total current is this plus this. So what I'm saying here is there are 2 different ways in this particular case to calculate the total current. One is I can use Ohm's law and apply it directly if I knew the total resistance, which I've calculated, or I could use Kirchhoff's law and Ohm's law to calculate, because I know the total, this plus this equals this. And how do I apply Ohm's law to calculate the current through here? Well, the theory of Kirchhoff's law is the fact that the voltage drop across this and the voltage drop across R1 and the voltage drop across R2 are the same. So I know the voltage drop and I know the resistance. I can easily calculate the current. So the current through R1 is VR1 divided by R1, and I know that VR1 is 10 volts because the source voltage is 10 volts, divided by the resistance is 100 milliamps. I can do that again down here, and I can say this guy is VR2, which is, again, the source voltage, divided by 57, and now I have this plus this. When I add them together, I get 279 milliamps. There you go, nice and simple. So I can calculate it one way or another way, and you will find, especially when you get into parallel series circuits, there are like so many different ways to solve these things, but they're the exact same value, and we did it 2 different ways. Okay, good. So now let's say you're designing a circuit for an automobile and you must calculate the fuse required for the circuit. By the way, this is on the exam. And there's a very good example of me doing it under the lecture material, and you will see that, and it's there, and just watch that video. So what I'm saying here is that This fuse is protecting all of these lights. I have to calculate how much current all of these lights are drawing from the battery, and then I can select the right kind of fuse. So this example is going to give me some values, and let's just say over here that each headlight has a resistance of 4 ohms and each taillight has a resistance of 10 ohms. Now it's interesting to note that a certain amount of students in my class, they add up the resistance in series. I guess they didn't watch this video, and they didn't go to the parallel lecture. Dude, if this is 4 ohms and that's 4 ohms, the total resistance between the two of them is actually 2. You can do the math, but it is. If that's 10 and that's 10, the total resistance here is going to be 5. Okay, so now the source voltage is 12. So what I'm going to do is I'm going to find the total resistance by just using the formula, this, because they're all in parallel. And then I'm going to find, what are the 3 lines at the bottom? Oh, I'm sorry. That's a really good question. Okay, guys. So what I'm saying is this is a common ground, and we use common grounds to indicate this. For instance, like that's common ground. For instance, let me take a look at this circuit over here that I drew. This circuit has a line going all the way through, indicating that this is connected. If I just put a ground symbol here and a ground symbol here and a ground symbol here, it means that they're all connected. It saves me actually drawing a line going all the way back to the battery again, because in a car, which is pretty cool, the actual metal of the car is the ground. The metal is connected to the negative terminal of the battery. So when I'm running power to a light, all I need to do is run one wire, because then I can just take a wire off the light and just screw it right to the body of the vehicle itself, which is the ground. So we call that a ground symbol. Very good question. Thank you for that question. So, so what do we do first? You know what? If I want to know the total current, I'm going to find the total resistance. Okay, let's go through that. Let's find the total resistance. Calculate the total resistance. Okay, so it's going to be 4 to the negative 1 plus 4 to the negative 1 plus 10 to the negative 1, 10 to the negative 1, all to the negative 1 ohms. Okay, so now that's my total resistance. My next step is to just calculate the current, because total current is the voltage source, or you could say the total voltage, but we say the voltage source divided by RT. And in this case, it's 8.82 amps. So if I get an 8.82 amps, I'm going to try and maybe get a 10 amp fuse. I'm going to overrate it, because if I actually went out and found a fuse, which doesn't exist, I could probably have one made. It was exactly 8.82 amps. It would blow, because a fuse will blow at its threshold. So if you have a 10 amp fuse and you put 10 amps through it, it will blow. If you put 9.5 amps through it, it will not blow. So I want to get something that will blow. If this fails for some reason, the current's going to go more than 8.82, and then it's going to blow. So I'm going to use a 10 amp fuse. Okay, good. Now, this is pretty cool. This is like a notation that we can use, and I don't need you guys to understand this notation. Oh, by the way, there's this thing called resistor. Okay, let's move forward. The reason I'm telling you this is because it comes handy when we're doing series parallel circuits that we will do after the break. Okay, good. So it's just a resistor notation, but essentially you can say, in this case, this is in parallel, but that's in parallel, but that's in parallel. You can use the resistor notation, but I need you to always write the formula, because a formula is different than resistor notation. Good. So we know that that's a resistor notation. All I need to do is show you right now is this car circuit. There's an example of this car circuit. It's an awesome circuit. And these are applications of parallel circuits. In a house, it's parallel circuits. And these are current dividers. Now, current dividers are something cool. Now, you're going to study the current dividers when you watch the video on the review, okay? So I want you to watch the video on review and go through the current dividers, because current dividers are pretty cool, and power. So again, I don't have any more time. We had the co-op, but I'm saying there's a lot of material about power in parallel circuits in the review, okay, guys? So I'm not going to leave you hanging. If you guys need more information about this, then I'll talk to you about it, whatever. But if you have any questions, let me know. Now, this is an intense circuit. I'm not leaving you hanging with this circuit. I'm going to say there's a lot of work you need to understand in this circuit, but don't worry, because I'm going to go over here and I can share my screen here. Okay, good. So this thing here is all about that circuit that I just showed you, okay? So I'm talking about the whole thing. So watch that video. I'm not even going to go over that in the lecture, because there's a lot of material there. Okay, guys, that's it. Thank you for watching. and good luck with the exam. And I'm going to let you guys go, and I'm going to get to some questions. Okay, thanks.